Okay, so we're talking about waves here. We've already talked a little about the basics of waves. Let's talk about the interactions between multiple waves and what happens when they're in motion. So just a little bit of review. We're looking here at a wave. We have three cycles here represented. Remember, our amplitude is how tall my wave gets, and the particles vibrate up or down what their maximum and minimum height is. Wavelength is one complete cycle. It can measure from crest to crest, or from trough to trough, or crests to the tops and troughs to the bottoms. This particular wave, we're showing a wave moving to the right. So this would be a transverse wave, because if its motion is to the right, it's vibrating up and down. Now, we've also talked about frequency. Frequency is how frequently a cycle shows up. So the shorter its wavelength, the higher its frequency will be. They're all jammed together versus a lower frequency. Frequency is directly proportional to energy. We've also talked about the velocity of a wave, or velocity is frequency times wavelength. Now, let's define wave reflection. This is a specific interaction that happens whenever a wave bounces off material and goes in a new direction. So there's lots of different types of reflections because of the different types of waves. Now, the wave that reflects is exactly like the original wave. We have the same wavelength, we have the same frequency, it's the exact kind of wave, it has all the same properties. The only thing that's changed here is the direction. A good example is like an echo. So you yell out, you get the same sound, you get the same pitch, you get the same noise that comes right back, but it's changed direction. It's no longer going forward, it hits, it bounces, and it's coming back at you. A mirror is another good example. The light waves that reflect in the mirror look exactly the same in the mirror as they do in the original, but they're coming from a different direction. That's the only thing that happens in reflection. Now, whenever we have reflection at angles, reflection at an angle always bounces off the same angle it comes in at. The angle it comes in at is called the angle of incidence, and the angle it leaves at is the angle of reflection. Now, whenever we measure this angle, we have this solid barrier here off to the side. That's our reflective surface. Reflective surfaces tend to be hard and smooth. Whenever we measure the angle, we draw a normal line. A normal line is straight perpendicular at a 90-degree angle, straight out from it, and that's what we measure the angle from. So the angle of incidence, the angle of reflection. In reflection, the angle of incidence and the angle of reflection are always exactly the same. If you think about this, this makes sense. Think about throwing a tennis ball against the wall. If you throw the tennis ball directly at the wall, the tennis ball comes directly back at you. If you throw the tennis ball at a 30-degree angle at the wall, it bounces off at a 30-degree angle. Light waves, sound waves, all kinds of waves reflect just like you would imagine. Okay, here we're seeing an example of reflection. This is an echo. So we start here. Whenever this person talks, the wave goes forward, hits a hard boundary, and reflects back. The time here measured is how long it takes. If it's very short, sometimes we hear it as a reverberation, meaning it's where we're hearing the same sound twice. Typically, we'll see a case like here at the bottom. Now, it's important whenever you're calculating these is this distance from the source of the sound to where it's reflected from. The wave actually travels twice that distance because it travels there, it reflects, and it comes back. So whenever we're using something like velocity equals distance over time, and they ask how far away it is, and you look up the velocity of sound, say it's 340 meters per second, and you use the time, the distance that you find, that's the distance there and back. If they only ask how far away the cliff is, or they might be like yelling down into a cave, how deep is the cave? You're going to have to take half of that distance because they only want the distance to the bottom, not the distance to the bottom and back up. This is a very common example of a classic physics problem. Okay, we also have wave refraction. Wave refraction is a little more complicated. It happens when our wave moves from one material into a new material. Because it's moved into a new material, the wave is going to bend. Now, the reason this happens is because the speed of a wave is constant as long as it stays in the same medium. When I say medium, that's the material it's in. So the speed of light, that 3 times 10 to the 8th meters per second we've been talking about, that's the speed of light in a vacuum. The speed of light would be different if we're talking about air or if we're talking about glass. So whenever we move from one to another, from one material to another material it's moving through, that changes our wave speed, which causes it to bend and change its direction. In our example here, we have this wave, presumably a light wave moving through air, and this looks like some kind of lens, some kind of glass lens perhaps. And whenever our wave moves through it, the light will slow down, which will cause it to bend. Because of the shape of this lens, it's going to cause it to bend inward. So they cross when they move across the boundary, and it's the different density that gives them the different speed. Eyeglasses are an excellent example. The prism's a good example. Now, because each of the different colors is a slightly different frequency, a slightly different wavelength, whenever they move from the air into the glass, they're going to bend at a slightly different angle. Because they're building at slightly different angles, that's what causes this white light to be separated. This idea of refraction of light in a pool is a very common test question that comes up with, because swimming pools appear more shallow than they actually are because of refraction. They'll also use this exact same idea with like spear fishing or something of the sort. If here's the surface of my water, so here's air above and water below. The speed of light is slower in the water than it is in the air. So whenever we see the light coming out, so if we're standing up here, and we see a fish below the surface of the water, whenever the light hits our eyes, we see it as if the fish has come from there, because the light has hit right here. Now, our eyes assume that the light has come straight back at us. So we imagine if the light came at us like this, that it came straight back out, and here's where we would see that fish. Our brain doesn't imagine this refraction, because what happened is the light didn't go straight. Whenever it went from the water to the air, it actually bent out. So if we imagine this normal line right here, whenever we speed up, we bend away from the normal line. Now, because it's bent, the fish is actually down here. So this would be the sun up here, okay? There's my sun. So light comes from the sun straight, hits here, bends down, hits my fish, reflects off of it, and comes back here and bends back to my eyes. So my eyes follow this path, seeing it here. But its actual depth is down here, because I'm not accounting for the bending. Now notice I said that the light reflects off the fish. Everything reflects. That's how we see everything, because there's light reflecting off of it. Okay, whenever we're talking about refraction here on the left, we're looking at this one block here, presumably of glass or something like that, and our ray is going through the air. Whenever it moves into the glass, it slows down and it bends towards my normal line. My normal line is this dotted line here that I've drawn. It's always perpendicular to whatever the substance boundary is at a 90-degree angle. Okay, the two are crossed. So whenever moving into something that goes slower, we bend towards. Now whenever moving out, we speed up, we bend away. Now notice that the incident ray coming in and the refracted ray coming out are perpendicular, the beginning and the end. It's only in the middle that it's kind of bent. We can see that here zoomed in. One way you can think about this is we're going for something less dense, the fast density. You can think about like a car. If the car is going straight on the road, whenever it hits the mud, whenever this front tire hits, going through the mud, the more dense is going to slow down my object. So this right tire is going to be moving slower, but the right tire hits here first. When that tire is moving slower and the left tire is moving faster, that's going to cause the whole car to turn. And then once both tires are at that point inside the mud, that's when they're going to start moving straight again. So it's only crossing the boundary whenever the speed is changing that we actually get that change in speed, that we get the bend. Once the entire wave has moved into the new medium, the new material, then it'll move straight from there on out until it crosses a new boundary. We can see it here a little bit closer where it's graphed out. Here's our ray coming in when it's in the air, and then when it's in the glass, it bends because it's at a different velocity now. That's what's causing that change. Our next wave interaction is called diffraction. Don't be confused because we have words that sound similar, refraction and diffraction. Diffraction happens because a wave bends around or goes through a hole in a material. There's some kind of opening, the space has increased for the wave to go through, and so when there's this blank area the wave is moving by, it'll spread out and occupy that area. So the wave is moving forward, it comes to this barrier, and it starts to wrap around the edge, as if this corner here is a new origin for a new wave, and it starts spreading out. Or if we have like a window or a door, and sound is going to it, the sound will start to spread out from this new point as if it's a new origin. Diffraction does change the direction and the shape of the wave. Because we're staying in the same material, though, we still have the same velocity. We experience this all the time, hearing around a corner through a cracked door. Here's an example of diffraction. If you imagine it's just a picture, so here would be the origin of the wave being tapped here. Imagine this is water, and it's tap, 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 tap. Every time we tap, there's waves radiating out. Now you can see some of the waves have reflected off of this hard boundary. You can see those circles right there. See them coming back? Now the waves that are going straight out, they go straight, 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 they hit this, and as soon as they move through here, they keep going straight, but they also bend out as if it's a new origin. Notice how the waves that look like going off from this side of the origin looks the same as when they're coming out of this circle. They're diffracting through there. Natural frequency. Natural frequency is the frequency at which a system oscillates, means vibrates when it is disturbed. Every material has a specific natural frequency that is defined by the object itself. This comes up when we're talking about resonance. Resonance is when an object is forced to vibrate at its own natural frequency. It causes the amplitude to increase. These are some really common examples, is like pushing someone on a swing. They naturally start going at that same frequency, that natural frequency. That's more periodic motion than wave motion, but gives the same idea. Guitars, pianos, those kind of musical instruments are best examples of resonance. Whenever you pluck a guitar string, the guitar string is vibrating. It causes the entire body of the guitar to vibrate, and they vibrate at a very specific frequency that depends on the type of string and depends on how tight we have that string. That's how we get those different notes. That's how, if we can get our sound waves to match the natural frequency of a wine glass, we can get it to break. There's also the famous example of the Tacoma Narrows Bridge, which is a very famous example of resonance. So this video looks really old because it is really old. This guy is actually the guy who wrote our conceptual physics book. His name is Paul Hewitt. He's extremely cheesy, but he's a decent physicist. We're talking about resonance.
If this room were filled with ping pong balls and I had a big paddle and I shook it back and forth, I'd send vibrations through this ping pong balls. Same type thing happens when I strike this tuning fork. This vibrates back and forth and hits the air, and the air vibrations, that's what we pick up the sound.
Notice whenever he grabs it, it stops vibrating, you stop hearing the sound.
I have a fork of frequency sensing. Watch this one. Like this one, and this one vibrates. Or
you know that the other one was making the sound because he grabbed the first one. It couldn't be making sound anymore because it would be vibrating.
as long as the frequencies are matched, I can get the vibrations to cascade back. It's called resonance. Huh? What happens if this fork has a different frequency? All right, let's try that. Yep, nothing. I have to have this frequency the same as this to pick up the vibrations from here. That's what happens with the radio set. The radio signals are coming in, and you change the frequency of the radio set so that it matches the incoming frequency. You got it. Physics. Yay.
He's kind of a crazy guy. Interference. Interference is something that happens whenever we have two waves that overlap. Depending on how they overlap, depends if it's going to be constructive interference or destructive interference. Constructive interference, when the two waves meet, they combine and form a large single wave. Sometimes we'll call the one piece just one pulse. We're looking at just one piece of a wave. Constructive interference happens if we get crest to crest or if we get trough to trough. The same sides are lining up. So we can see this here. Two crests moving towards each other. When the two crests overlap, the two crests add together and combine. Now, interference is only something that we observe. They haven't combined into one single wave because you can see they'll keep moving apart and the original pulses are preserved. Destructive interference is when the two pulses meet and they cancel each other out. So now we're not getting the same parts meeting, we're getting opposites. Crests hit troughs. So the crest and the trough meet there and they're counteracting each other. You can think of it in terms of vibration. So the crest is where the particle vibrates up, and the trough is where the particle vibrates down. So if the particle here in the middle is being vibrated up and down at the same time, it's the exact same amount of vibration, it's kind of gets stuck there in the middle. Now again, my waves aren't destroyed, they're not gone permanently. It's just when they're overlapping. Because if they keep moving and they move away from each other, they will appear once again. So these two waves are lined up perfectly so that they will interfere destructively. Because where the crest of one trough is at, where the crest of one wave is where the trough of the next wave is. Crest to trough between two waves is how we get destructive interference. So we're looking at interference, it's really obvious on transverse waves, particularly looking at a graph. So here I'm going to use the red wave and the blue wave, and here's the green wave. The green wave is the wave that we see. It's only the wave that we observe. That is the interference pattern. It's not the real wave. The real wave is the red and the blue one. So here I have a red wave that has +1 amplitude on this crest. My blue wave has a +1 amplitude on its crest. Whenever the two crests overlap, I get a total of a +2 amplitude. Now if there are two troughs, I get the exact same thing. This is constructive interference. Now, if I look at destructive interference, I have a red wave that has a crest with an amplitude of +1. I have a blue wave that has a trough with -1. +1 and -1 combine to form this green wave right here, which is just perfectly flat. Remember, this is only an observed wave, though. Now, here I have a +1 and a -2. +1 and -2 ends with the green wave of -1. This this chart here might help you think about this. So two crests are positive, remember. Crest and crest, +1 and +1, gives me what I'll see in green, the +2. -1 and -1 is a -2. +1 -1 is 0, +1 -2 is -1. These are the four examples we just looked at. Think of it in terms of a graph where crests are positive and troughs are negative. If you get them to add up, the same kinds together, you'll get more. If you have opposite kinds, you'll get less. Constructive and destructive interference. If we look here at our example, we have water dripping from a faucet. We can see that the waves are going out, circular waves emanating from that point. I can change its frequency here. I can make the wave more frequent. I can make it less frequent. Now, all waves have the same wave properties. So I can look at sound waves. I can change the frequency of that my speaker is at. Now let me go here from this grayscale that represents how loud the sound is, to particles. Change the frequency so you can see it. Because remember, here's the vibration moving through it. And we can look at light. All following the same properties. Let's go back to our water. So I can take a barrier and I can insert a barrier here. So a solid barrier. So now my wave is hitting this barrier and it's reflecting off. See it reflecting off there? So I'll take the barrier out. You can see just the circular waves. Whenever the barrier is there, the waves hit and they're bouncing back. Now the waves are actually interfering with itself. This specific pattern we get, this is called an interference pattern. Now if I take my barrier and I open up this little spot in the middle, I can see the wave starting to diffract through, spreading out through that opening. And you can see that this spot right here is acting as if it is another focus point, another point where a wave is emanating from. Now, if I make it so that there are two slits in my barrier, you can see first of all the wave that's being reflected back. See, I'm getting some reflection there. But these waves that are coming through here, I'm getting two waves diffracting, but notice how they interfere with each other as well. Anytime two waves overlap, I'm going to get some kind of interference. The dark points here are where I'm getting constructive interference. The waves are adding up and getting even darker. The light points, we're getting destructive interference. The waves are canceling each other out. You can see I get the same types of interactions.